Hello, my name is Oliver Maiß, and I am the manager here at ECOROLL, the Research and Development Department. Do you actually know how to properly design notches and how to increase the lifespan of components by roller burnishing, especially in notches? If not, that's exactly what I would like to explain to you in the following video. Notches have enormous significance in mechanical engineering. I myself had to draw a gearbox or a component from a gearbox in the first semester of my mechanical engineering studies, and there I was repeatedly reminded of how important it is to consider the design or the consideration of notches in the design process. If we look at a gearbox as we see here in the picture, we can see them everywhere. Transitions from shafts to scars, different diameter areas. Everywhere we have notches that cause our component to actually fail at these points because we have a stress concentration here. As designers, we face the challenge of not over-dimensioning, but at the same time we must accurately predict the probability of failure. This means we are somewhat facing a conflict of objectives, and as designers we are not entirely sure how to handle this. For this we need frameworks. These frameworks are provided, for example, by the FKM guideline, DIN 743, or the FVA guideline. With these, we have guidelines at our disposal that allow us as designers to design these shafts. These guidelines, of course, take various areas into account. The notch shape first, of course, the material is also taken into account. We, from the mechanical surface treatment, also know that the surface and edge zone properties have an enormous impact on the lifespan, especially in the notch areas. And this is also considered in the guidelines. If we look at the areas of roughness, hardness, and residual stress, we see that the guidelines treat these with varying intensity. While roughness is considered separately as a parameter in all three guidelines, hardness and residual stress are only considered in the FKM guideline and also in the DIN through an additional factor. This means that there is no explicit mention of how large the residual stress value is, and thus the designer is left with only an estimation. This estimation is made using the so-called KV factor. The KV factor essentially tells the designer how much they need to reduce or increase their design so that the component still holds or no longer holds. Typically, stress ranges are specified here. This means that the KV factor is specified for shot-peened or roller burnished components in a range from 1 to 1.5, for example, in a guideline. As a designer, I am naturally responsible for ensuring that the component holds. So, logically, I design the whole thing a bit more conservatively. If I design it conservatively, I am more likely to use a KV factor of 1. And then, honestly, I can simply forget about the solid wood because it doesn't provide any additional value in my calculation. So what do I need to do to evaluate this value even better? This has been addressed by a research team from TU Chemnitz and TU Dresden. In a study presented at the VDI conference on shaft hub connections, Ms. Günther and her colleagues focused on how to better evaluate the various guidelines for rolled notch points, and I would like to summarize a part of this study for you here. Various experimental programs were conducted in the study. We have, for example, in the study the variation of the notch shape. An unnotched, a mildly notched, and a sharply notched sample were examined. The samples were tested under different loads. That means we examined a tensile compressive load here, a rotating bending load, and also a torsional load. In the study presented here at the VDI conference, only the material was 42 chromophore. In the QT version was examined. However, I also know from participating in the research project that other materials were also examined, which will probably be published at a later date. However, we also examined the diameter to take into account the dimension of the components. Diameters from 10 to 36 were examined here. And thus, a really very broad testing program was set up here. I myself have not yet seen any study that, especially with the various materials that were also examined, has laid out this broad testing program for roller burnishing. The samples themselves were processed with an EG5 tool using a 40 mm roller. As you can see in the picture here, the roller is designed to match the transition radius and is then essentially driven onto the cylindrical surface, over the feed across the cylindrical surface, through the radius up to the flange surface. it was driven over the component, we worked with a constant feed and always documented the force accordingly. After the processing, the surface roughness, hardness, and residual stress were measured and documented. The experiments themselves or the production of the samples were carried out by a contract manufacturer. So here too, in a series production under constant conditions with the same material, everything was documented properly and conducted properly from one batch, and care was taken to ensure that no additional variations were introduced. As a result of these studies, I have brought you only the part that is so relevant to us. Of course, you can look at the evaluation in the entire study. You can also take a look at the various other types of loads and test programs. Take a look at them once, but here are simply the two important results for the roller burnishing. These are the tensile compressive load and the rotating bending load, each for a sharp and a mildly notched sample. In the unrolled state, we see in both cases, of course, that we have with the increasing notch sharpness a reduction in nominal stress. That means our component can bear less load. However, what we see in all four tests is that through shot peening, we achieve a significant increase in nominal stress. Both in tensile compressive loading and in bending fatigue loading, we have a really significant increase. The entire effect is most visible in the rotating bending load with the sharp notch. Here, the highest stress concentrations occur. And here, the compressive residual stresses have the best and most significant effect. Simply put in terms of values, we have almost a doubling of the nominal stress here. Do we still have a nominal stress with the unrolled sample? Of approximately 280 MPa, we are already over 500 MPa with the hardened rolled sample. So nearly a doubling of this value indeed. This is an excellent result for the hard rolling and shows the great potential. If we can now take this into account in the design and have guidelines as a tool to already factor in this great potential beforehand, then we can of course also start to dimension components smaller, save resources, reduce the CO2 footprint of components, and truly achieve an effect. That adds value, both for the wallet and for the future, for the ecological system, the resources of our planet. With that, I am at the end of this short video. I sincerely thank you for your attention. If you have questions about this or other topics, you are of course welcome to contact me or my colleagues at ECOROLL.